right. So, let's see, where do we want to begin? Let's get into some notation and some vocabulary. Ancient Israel took geometry, the concept of the slope of a line, or rather the line, a point, either on a circle, it only touches at one single point, doesn't pass through it. A secant is similar. However, secant does either go all the way through chords. Secants and chords are very similar in that concept. Most people consider secant as something that can pass through your hand, pass through the chord, whereas a chord is a linear term for only 2 points on one side of it. Sure, it could pierce more than 2 places. Yeah, it's just the idea that you're connecting 2 points on a curve. Okay, namely these 2 points. Gradient. Gradient is a fancy term for slope. This is often used in the UK. This is us. This uses slope, but everybody else uses. And since we are an IB World School, expect to hear the term gradient probably more often than you hear slope. But we teach you slope. It means it's the rise of a line. It's the amount of inclination of a straight line. All right. Just so that I don't truly piss off a whole lot of people for that one. All right. Also, instantaneous rate of change. This is one of the most important applications of calculus, specifically the first part of calculus, differential calculus. Instantaneous rate. Let's just sample. I'm talking about the sun in the sky. Okay. Fluffy. Play nice. Okay. Yes. All right, so that is my really bad interpretation of the height of the sun along the horizon. We might actually have the horizon somewhere like there, depending upon what latitude you're at. Okay, so sometimes it's above the horizon, sometimes it's below. Now, if we look at this, if I'm at this particular time of the day, the sun is only a little bit above the horizon, okay? But here, it's zenith, you know, near noon, roughly, what time of the year you're at. All right. Now, my question is not the actual as the height of the sky, but how fast it's rising or setting. At this point, right here, is it rising or setting at all? You know, if I look at it and I watch it for a couple of seconds, it looks like, what does it look like? Is it going up or is it going down or what? It looks stationary for just a tiny little bit and then it starts going down again, right? Slowly going down. If you think about a ball bouncing, okay, simple power bouncing. You take an object at the top of its perigee, at the perigee, it is instantaneously, for that just one fraction of a second, it's standing still. It's not going up, it's not going down, and then it begins to fall. But as I let go of it as this pen leaves my hand, it has all of its energy in terms of motion, if those of you who've taken physics. All of its energy is kinetic. It's all motion. It goes up, gravity slows it down, and that kinetic energy turns into potential energy. When it finally gets to the very top, all of its kinetic energy has been converted into potential, and then that potential begins to transform back into kinetic, and it speeds up as it falls. And when it hits my hand, it hits my hand with the same speed that it had when it left. Okay, so at the very bottom, right here, and you can see it, it's climbing. The sun is getting higher and higher, faster at this region. It's moving faster than it's moving when it's up here. Does that make sense? Not height, but speed. Okay? And how we can tell that is by first looking at it. And zoom in a little bit. As I move from left to right, that height increases quickly. Whereas up here, as time progresses, my height doesn't change very much at all. Speed slower. Okay. Are we following along this? Okay. Well, that's wonderful. But in order for me to get this speed, I first have to understand what it is that I'm looking for on this graph. Because what I'm trying to do is I'm trying to find the slope of the gradient, the slope of the tangent. In this case, let me switch colors. You see, it's that slope right there, that green line, is very shallow. It's not growing very fast. And then it reaches its top, badly drawn, at the very top of it, and then it begins to fall again. At a point, as that point moves along the line, the slope changes. And what we want to do is we want to be able to find that slope. And it depends upon the curve. If I have a curve that's and doesn't change very much at all, then I'm not going to be seeing a lot of difference in my tangent. Whereas if I have a function that looks more like, that, my tangent is going to go from very negative to 0 to very positive very quickly. So what slope it is depends upon the function itself. All right. So there has to be a way to go from a function of a variable and play with it in some way to have it spit out the slope of the tangent at a given x. That's what both Newton and Leibniz were working on. And that was the birth of calculus. So how did they do it? The first thing that they did was they went back to the definition of slope. That's a bad one. Okay. From here, we will derive the derivative. That's right. And it's the derivative for this reason. Derivative is the first function that we work with in calculus. The next one that you're going to do after that is called integration, which is very much related to differentiation. You're going to do both. So from this, all right, let's take a function. I have 2 points, x2, y2. Write these lightly, you're going to erase them in a minute. x1 and y1. So this point right here is what? On the x-axis, directly underneath that point is what? x1. Okay? And this is x2. Okay? And the height of this guy is y1, but I don't like using y's. I'd much rather use a function. So, because I want to be able to plug things in later on, so I'm going to go back to f of x notation. So this, let's erase. Told you to write it lightly. Is f of x, 1. And this is f of x2. Right? Wonderful. Okay. Now, what they both thought about was if we could, you see, what I really, really want is I really, really want this. Let me change my color. I want that function over that red line. The honest to God slope, the real honest to God tangent. That green line is a reasonable approximation, but it's an approximation and it's not fantastic. But what they thought about was, if x1 and x2 were really close to each other, then my approximation of that green line's approximation would be better, right? And I made a nice little applet for you to look at that. All right. So here, and if you guys don't mind, just for visual purposes, I'm going to kill it. All right. What I've got here, and actually I think I'm going to need to zoom out a little bit. Where did you go? I lost my slider. Where's B? What's that?
So when is it coming back?
Oh, right, yeah. Let's see if there you are. Okay, better. Sorry, I lost my slider there for a minute. All right, so please take a look. All right, now, shh, guys, come on now. All right. Now, I think I can. All right. If you guys can see, I have this parameter is the function x squared. And what I've done is I said to myself, all right, I am interested in finding the slope of this curve at the point x equals 1. Okay? And what I've done is I've created this bottom red segment right there is h. You're going to see that variable a lot. That is the distance between my x1 and my x2. Okay? So my h, this is going to really be bad, but we're going to do it anyway. This I'm defining as h. So now what we can say is we can replace x2 with x1 plus h. And now, since there's only one x involved in this thing, we can drop the subscript. Now, what we have instead, actually, we can change this whole thing. I know, I told you to write them lightly, you're going to erase them. You don't believe me. You don't believe me. So that becomes my new set of points. Because now what I've got is I've got all of this thing in terms of two variables, x, which is what I want, the location I'm interested in, and h, which it changes. And as h gets smaller, my approximation should get better. Now, what we're going to do is we're going to take a limit as h goes to 0. Because as h gets to 0, my green line is going to get closer and closer and closer to the red line. Do we see where we're going with this? Watch. All right. So take a look. At 3, my slope is 4. Can we all read this, or is it too small? All right. So here I have x plus h, function at my new point, and 1. Now, take a look. Oh, stop. Take a look at what is happening to my slope. It's getting smaller. And what is it approaching? H is approaching 0, but what is the slope approaching? You can see, even here, it changes pretty fast. And now it's slowing down. And in fact,
what value is lowercase b?
Oh, b is just the variable, the distance between. I probably should have called it h. All right. Now, so let's go back here for a second. So, to find my slope, I'm going to set up the slope equation. Now remember, that was y2 minus y1 all over x2 minus x1. Don't write that down. But now, this is just the slope between 2 points. But now we've introduced this other notation, x plus h, f of x plus h, f of x, and all this other stuff. Let's plug all of that into my slope formula. So what's my numerator going to be? F of x plus h minus f of x. Who's that? Oh. All over what? Okay, and we can do a little bit. We can do a little bit with my denominator. Yeah, it's also addition and subtraction, so I can simplify the denominator a little bit to just plain old h. And this is the definition of a derivative. Well, we're going to do lots of examples, and we'll be spending probably 180 days working on this. So, Yeah,
Wait, how did you get this?
because it was x minus h. So it was x plus h minus x. That being my x2 and that being my x1. But I can simplify. This is one of the fundamental theorems of calculus. All right. Now, let's actually use it. Because remember, you can't divide by 0. So if this thing actually makes sense, and we're not just pulling this rabbit out of our hat and saying it works, h has to go away. Because if h is left over, once I attempt to take that limit, I'm going to require that division by 0. So somewhere throughout this whole thing, you know you're on the right track if your h goes away in your denominator. Let's take some examples and see what happens. All right, let's principles. Something. All right. Do all right. Now, if I am interested in finding the derivative, now, I'm going to attempt to do this by first principles. That term you'll hear a lot in science and in math. In chemistry, that term is, there's another term for it, it's called using Monte Carlo methods, where you're basically saying you're not taking anything for granted. You are using the basic simple rules. You're going back to the, like, in a geometric sense, it would be like going back to Euclid and building everything back up from scratch. Okay? And yes, you will not have to do this very many times, but you do need to know how to do it. So we start with the definition of a derivative. And we plug it in. So this h minus f of x over h. Now we substitute. And so now I have 7 x plus h squared minus 7 x squared all over h. All right, let's expand. I did it again. I always do this. I always forget to put my limit part on there. I don't know why. It's a bad habit. Don't. Now we distribute and simplify. Simplifying. Let you guys catch up on that. At this point, we can breathe a bit of a sigh of relief because we can get rid of that h in our denominator now. Okay. All right, now, I remember I got into a furious argument with my instructor when I learned this. At this particular step, yes. Sorry, good catch. Thank you. This is when the fairness that thing that changes. In this case, it's H. Good catch, sorry. I got into this argument with my professor, with my teacher at the time. Of course, you certainly do. I really had a problem with this and then that. Because what's going to happen now is we're going to take that limit, and what's going to happen to that 14x plus 7h?
It's just going to be 14x.
Right. Because, in effect, what I saw was I just plugged in 0 for h. Taking the limit was just a fancy euphemism for substitution, but that's not really true. Because I said right here that h wasn't allowed to be 0, and then just 5 seconds later I plugged in 0 for h. And I'm like, wait a minute, something's fishy in Denmark. Because when you take that limit, what's really happening is, no, you're not plugging in 0. What you're doing is you're walking very close to 0. You're getting as close as you possibly can to it. And basically what happens to that 7h? It becomes nothing and falls away. So, this is the derivative, and this is how we write it. There's several different notations for this. This is most common because it's easy to write. We put that little tick on it, saying it is a derivative of f. However, there's a more formal definition of notation. Yes, it does. And sometimes you are called f prime. Yeah, but often it's just called those, and later on we'll talk about the second derivative, when we do a bit of that. So we do it twice. And it means something else, you'll see. F double prime. Because math is fun. All right. You can also see this notation. Okay. This is and 3x. Okay. Theorem 3x. And this means the derivative of rate with respect to x. All right. Now, this was another place where I thought to myself, what is this notation? Why do I respect x? It doesn't make sense. What it means is x is the thing that is changing. And as x changes, x is the independent variable. As x changes, y changes. Calculus is all about change. How does something change when I manipulate a variable? Here's an example. The price of a stock. Let's just say you own a stock in a flower bed in a flower company. Okay, you know, you own stock in that, whatever. Guess what? As you get closer to Mother's Day, you're going to get more profit. Okay, as you get, you know, further away from Mother's Day, your profit margin is not going to be as high. The time is changing. Profit with respect to time. Independent, dependent. Yes. Like, because, for example, I could change my profit by changing the price of my roses. Okay, if I raise the price of my roses by 10 cents, I'll make some profit. If I change that even more, let's just say I add $1 to every rose, I might make some profit, but I'm going to lose a lot of customers. So there'll actually be kind of a push and pull going on there, you know? So it wouldn't just be a straight linear climb. I mean, I couldn't make a rose $100. It wouldn't work. Hi. Oh, thanks, no problem. Nonetheless, so the concept with respect to X is the concept of saying, how does something change? And what does it change how does the Y change when I change my X? Okay? All right. All right. So now that I can get this. All right. Now that the main office is happy. All right. Why don't you try all right, let's try this. Fine. Try this one again. I didn't get this very, this the first time I did it, so good try. So now, what happens when h goes to 0? -1 all over x squared. Okay? And this is, well, 1 over x squared is the derivative. If you're taking the limit. Yeah. So. Sometimes you'll even see the following notation. Of because what this is saying, this is the derivative of this guy with respect to x. So this right here is the operation, kind of like saying, I mean, operators are things that take in something and spit out something else. Okay, actually this is a functional, which is a kind of operator. But where you take in a function, it spins it around and spits something out. A square root, same thing. Takes in a number, spins it around, spits something out. Okay? This is the derivative. And then the one over with respect to. Okay?
can just use the function.
Yeah, there are different ways of writing the derivative.
You can just use a prime.
Yeah, but you need to be able to know what it is when you see it written that way, because you will see it written. For example, prime of x is very often used as shortcut notation. But formally, it's d over dx. Okay. And when, if you ever take a course on differential equations, you will have functions that have the derivative in the function. For example, air resistance. Right now, if I drop this pen, there was air resistance, but it was very little. Okay, because this thing wasn't moving very fast. But if I dropped, well, a piece of paper has more air resistance because of its surface area. But for example, if I throw a football, there's a little bit of air resistance. If I shoot a bullet, there's a lot of air resistance because the bullet is moving faster. In that case, the speed of the bullet determines the air resistance. Okay, so that's why they call it a differential equation, because you're taking a derivative inside the equation itself. Okay. Friction is another one too. The faster you move, the more friction there is. Okay. As long as you're not going really, if you're going really slow, that derivative piece inside the function it becomes very, very small. But if you are moving really, really fast, you get a lot of friction because the speed is greater. Okay. And that's down the road, but really cool. All right. Now, let's throw some more examples at you. Let's try, we're going to try a fancy one. All right, I'll leave fancy for homework.
Yeah.
You want to do one that's fancy?
Yeah.
All right, we'll try this one. All right. Try that. All right, so that's the magic trick. And now we simplify. We know that the numerator is going to multiply out, and you end up with that's what happens to your numerator. Now I can drop the parentheses, distribute the negative sign, and go from there. Simplifying my numerator, yeah. Bottom one should be a plus. Yeah, it would suck in a minute if it wasn't. All right, we'll find out why. And now my numerator collapses nicely. Yep. My numerator reduces to that. No, we got rid of it. Well, we got rid of the coefficient. Right, but that's okay because it's not alone. And And now once I take my limit, so that's it. We've from my numerator down to my denominator. And we say that x shouldn't be -2, but that goes without saying for completion's sake. Okay. It's dynamic. Yes. Because there's -2 going to be taken, would be divided by 0. And in fact, I could probably say that x is strictly greater than -2, because if it was less than -2, we would have an imaginary number, which we're not interested in an imaginary slope. Okay, now we would be remiss if we ignored our friends in the trig universe, the derivatives of trigonometric functions. Alright. Before we do this, we have to first look at two specific limits and remind ourselves of some trig identities. The two derivatives, or the two limits that I want us to look at are these functions. These are the two functions that I need you to believe in before we can do them in general. So first, let's take a look at these functions. Made a nice little picture for you. All right. The red line, the red curve, is my cosine. The green curve is my sine. Sine of x over x, and cosine minus 1 over x. Okay? Now, at 0, first of all, if we look back at our functions, looking at these two functions, at 0, are they defined? No, because you're dividing by 0 again. But, just by inspection, what is the limit of cosine, this green curve? What is the limit of this curve as x approaches 0? 1. Okay. And the red curve, when x approaches 0? 0. All right, good. Now that we have those under control, okay. I need you to know these because I'm going to use them in a minute. Okay? They're not particularly fancy or special, but we need them. Okay? And a trig identity that's very useful, we're going to use in a minute. This one? Yep, lots of fun. Gotta love trig. Getting triggy with it. Now, So what we're going to do is we're going to see if we can find out from first principles what the derivative of sine is. Or better yet, let's use some better notes. This is our job. So we're going to use the definition of a derivative and go ahead into it. Actually, you probably can do it on your own, but probably. Yeah. That's the person. Thank you. I have a grammar Nazi in class. Wonderful. Use where your H's could maybe go away.